Bear with me as I complete my notes here. This is going to be an attempt to demystify the low-pass filter. This is going to be a mathematical derivation of a simple single-pole passive component low-pass filter where R1 is equal to 10 k ohms and C1 is equal to 0.0159 microfarad. Here's some things to know. Or to remember. Which is pretty much the reason for this video, so I can refer to it later in case I forget, or anybody can refer to it in case they're just interested in low-pass filters. The first thing is, you often see J, the imaginary number, is equal to the square root of -1. It's more correct to say that J squared is equal to -1. Second, capacitive reactance is equal to -1 over 2 pi Fc and not 1 over 2 pi Fc, which is, sometimes you see that in videos or books where they neglect to put in the minus sign. Also, sometimes you'll see this formula with an omega in here in place of the 2 pi f. That's pretty much standard in many of the engineering textbooks. Also, the equivalent of resistance for a capacitor, or the impedance of the capacitor, that formula is equal to J times the capacitive reactance, X of C. So that's sort of the equivalent of a resistor for a capacitor, or is the equivalent. Also, the voltage gain formula in decibels is going to equal, or does equal, -20 log times the absolute value of the input voltage divided by the absolute value of the output voltage. Now, first of all, why is it -20 and not +20? Because we're looking for the input over the output. If it was the other way around, if we were looking for the output over the input, or the gain of the output over the input, you would replace the minus with the plus sign. So once again, if this formula, if we were looking for the output over the input, then we wouldn't need the minus sign. Now the question is, why go input over output as opposed to output over input? Well, number one, it makes the math cleaner. That's pretty much the main reason. Also, it does have the effect of reversing the graph. So it affects the graph and it makes the math cleaner. That's all. There's no real other rhyme or reason for it. Okay? Now, here's the circuit. First thing to note about this circuit, if you were to take this resistor and put it up like this, rotate it upwards, and have the resistor up, and replace C1, let's say, with R2, as I have right here. What you end up with is a straight-on voltage divider. You see this everywhere. In the upper division engineering books, I mean, this is something you can't get away from. Now, if this R1 and R2 was the total pi, you ask yourself, what part of that pie do you want to take a bite of, or a nibble out of? What part do you want? You want this part. That would represent R2. So the formula R2 is divided by the total pi, R1 plus R2. Keeping in mind that this R2 is the equivalent of our C1, or will be the equivalent of C1 when we, and then multiply that by Vn. So this formula right here, R2 divided by R1 plus R2 times Vn, is our template. This is our template, and it's a straight-on average, everyday, nothing spectacular about it. It's just a straight-on voltage divider. R2 divided by R1 plus R2 times Vn. So the first thing I'll do is we need to write down what is the output of this circuit. What's the output of the circuit? V out. Well, using this formula, it's equal to R2 divided by R1 plus R2, but in this case we don't have an R2, we have a C1. Here is the equivalent of the resistance of a capacitor. This is it. So you would, think you could preliminarily write it ZC divided by R2. I'm not sure that's on the screen or not. R2 plus ZC, which is the equivalent of this. Then you would multiply that by Vn. So it's just a simple matter of then replacing ZC with the equivalent formula for impedance of a capacitor, which is right here. So I'll do that now. So then the formula becomes J X of C divided by R1 plus J X of C times Vn. Okay, so that would be the first thing. But what we're interested in is Vn over V out, and ultimately, of course, the absolute value of Vn over V out. But first, before we find the absolute value, the second thing is to rearrange this equation, and I will take the output and divide it, put it over here, and then flip this over and put it over there, and what you end up with is Vn divided by V out equals 1 plus our R1 resistor divided by J X of C. So this is what you get when you straighten out this equation. Now there's one thing wrong with this, is that it has we want to try to clean it up by eliminating the denominator. One thing you can do, or that the books show you to do, is multiply top and bottom by minus J. Minus J, minus J, and these are J's. They don't really look like J's, but so then now, thirdly, cleaning this up, Vn divided by V out. And I'm going to do one other thing. I'm going to replace the X of C, which is minus 1 over 2 pi FC, okay, with the R1 value, 10 k ohms, and the C1 value, 0.0159 microfarad. So I'm going to do two things. I'm going to clean it up after having multiplied through the minus J over minus J, and substitute in X of C with this formula, and replacing the C and the R that we get. Or let's say I'll do the previous version of that. Let's go like this. I'll go 1 plus J 2 pi F RC, and then fourthly, now we'll replace the values of R and C with this formula, and I get, after having already done the math, you get 1 plus J times 0.001 times F. Now I don't put in times or any indicator that these are multiplied. Just when they're together like this, it's all multiplying. So you multiply J times 0.001 times F, and this would be the straight on, call it a simplified formula if you will. This formula relates to these particular values. Of course, if these values were different, then this would be slightly different. But you're still gonna. But as you can see, we have nothing in the denominator, and all we have is this one j here. We got to get the point of this is to eliminate the j. The way to eliminate the j, I'll jump over to here to this what looks like Pythagorean theorem. Okay, but it's not really. It's what it is. It's what's called a Lagrange or a modulus plane or imaginary plane, where the horizontal axis is the real part and the vertical axis going up like this is the imaginary. Okay, so this would be equivalent of the resistor, and this, the horizontal axis, and the vertical axis would be equivalent of the capacitive reactance, or our imaginary part, the real part and the imaginary part. Now at this point you think, well, there's the formula, and just stick in the the equivalent of your A and B of this formula. Well, it's not that simple. This is not straight on Pythagorean. This is an imaginary. So what imaginary plane, triangle. So what you do is you take the real plus the imaginary B, you add them together and you multiply it by its conjugate. This is its conjugate right here. And this is the big ticket. This is the ticket item. This is the big mystery. This is the demystification of this. When you work that out, then you get this, which is very similar to Pythagorean. However, if I were to then relate this to this particular, in our case, simplified formula, you ask yourself, which is the real part and which is the imaginary part? The imaginary part has a j in it. So this is the imaginary part, and this is the real part. So quickly then, if I were to equate this with this, then you could go 1 plus j times 0.001 f times its conjugate, 1 minus j times 0.001 f. And when you do that, this is straight on algebra, a little bit of trig, and straight on algebra. That's all this is. When you do that, and the whole point, of course, of doing this is to find the absolute value. So fifthly, we're going to find V in, absolute value of, divided by the absolute value of V out. So we could eventually stick this into this formula right here. And that is equal to the square root, right? Because this is the square root of 1 plus, and I'm going to put the f in front, f squared times 10 to the minus 6. If you multiply 0.001 times 0.001, you get 10 to the minus 6. So this is really the most simplified in this particular case for a simple two-component passive low-pass filter. This is the formula. Then it would just be a matter of, after then the actual formula, sixth, is equal to, in decibels, dB, for the voltage gain, it's equal to minus 20 log, minus, because we have no amplification in here, and we're looking for V in over V out. Again, if we were looking for V out over V in, then you could replace the minus sign with the plus sign. It'd be positive in that case. 20 log times, instead, now we found our absolute value of V in over V out, which is this formula, so times the square root of 1 plus f squared times 10 to the minus 6th. Now, if you had a calculator and you plugged in various values for the frequency, like let's say 100 hertz or a kilohertz, 10 kilohertz, whatever the case might be, if you had, let's seventh, if you had log paper, we're going after that classical shape of the low-pass filter. If you plugged in, for example, this horizontal axis is the frequency, the vertical axis is the gain in dBs. Put voltage gain here. If you plugged in, for example, 100 hertz into here, you would get approximately 0 dB. So I'll put that in here right now. If you put in 1,000 hertz, then you would get, let's try this. This is the asymptote. You would get the classic, of course, the minus 3 dB. What's generally they call it the cutoff? It's not the cutoff. FC stands for corner, the corner frequency, or the break frequency. Break or corner. But it's somewhat of a misnomer to call this cutoff frequency because you're not really cutting anything off. Anyway, if you were to put 1,000 hertz in here, or 1 kilohertz, you'd get your 3D point. At the 3D point, there's a formula for the angle or phase, I should say, is equal to tangent, arc tangent, x of c divided by r. At this point right here, you're already at a deficit of minus 90 degrees. Okay, so the question becomes, what is the phase lag at minus 3 dB? Remember, Eli, the Iceman, this is for a series circuit. If we were dealing with a parallel circuit, then you would reverse this, the I and the E in this case, I-L-E and E-C-I. This would be for a parallel circuit. But nonetheless, for a series circuit, the voltage lags the current in a capacitor by 90 degrees. So we're already dealing with a 90-degree deficit. If you let the capacitive reactance equal, if x of c equals r, then this becomes 1, and the angle becomes 45 degrees, and so then it's just a simple matter of subtracting 90 degrees or and adding 40 plus 45 degrees to get minus 45 degrees. That's the phase angle at minus 3 dB. So that's essentially the low-pass filter demystified. And if you had a high-pass filter, it's essentially the same. Or if you were dealing with an inductor, it's the same. You just use the formula for inductance. If you had an inductor, then x of L is equal to 2 pi FL, and not minus. In an inductor, the inductive reactance is plus. In a capacitor, the capacitive reactance is minus. So, in conclusion, if you find this video to be helpful, leave a note or just put a thumbs up on it. And if you have any comments or suggestions, please feel free to drop a note. Thanks for watching, and have a nice day.